Hello everyone. Today we are going to talk about the interaction of electrons with the specimen. So let's take a look at what we have learned so far. So the story so far is that you have the electrons that are generated from the electron gun and they end up on the specimen with a diameter anywhere between 1 nanometer to 1 micrometer depending on the choice of your electron gun and the focusing and the lensing that you have done in the process, right? The current is typically anywhere between 1 picoampere to 1 microampere. In a well-collimated beam, the angular convergence is less than a degree, right? Typically 1 to 0.5 degrees. And depending on the acceleration of the electrons, they can have an energy anywhere between 1 to 40 kilo electron volts in an SEM. Okay, so the question that we're trying to answer is what happens once the electron hits the sample, right? Another thing that we are going to focus on is, are the signals generated in the specimen confined to the impact area of the beam impact, right? So the area of the beam impact is going to be, if let's say you have a beam diameter of 10 nanometers, so that's 5 nanometers in radius, so you take pi times the square of 5 nanometers, that is your area of impact in nanometers square, right? But is the interaction volume just confined to that little area, or is something else going on? So that's what we are going to figure out through this lecture and also in the next lecture. Okay, so when the electron hits the sample, a bunch of various processes occur. You have the generation of backscattered electrons, which are typically associated with elastic scattering. We'll talk about that. Also, you have secondary electrons generated, characteristic X-rays, visible light, Auger electrons. You have Bremsstrahlung X-rays. You have inelastically scattered electrons. So all of these things are related to various scattering events. So let's define what is scattering, right? So scattering is the interaction between the probe electrons and the specimen atoms. So if you have a crystalline atom, a crystalline specimen, then you would have these atoms arranged in a crystal lattice in order. Or if you're looking at an amorphous material, let's say a polymer, or just amorphous silicon or something like that, then there are still atoms which are randomly placed without any given order, right? And as the electrons hit the specimen, you have changes in the electron trajectory, changes in the electron energy, and as a user, we are going to monitor these changes to extract information of the specimen to understand and delve into the electronic and chemical composition of the specimen. Okay, so in order to understand the concept of scattering, you need to understand the concept of cross section, right? So the cross section is a measure of the likelihood that an event will take place. Okay, so the mathematical definition is Q is equal to N over Ni times Nt, where N is the number of events of a certain type per unit volume. So the event in this case is going to be scattering, and the amount of scattering that occurs per unit volume is what N represents. Ni is the number of incident particles per unit area. In our case, it's going to be the number of electrons that are coming over a given area. And Nt is the number of target sites per unit volume. So that's going to be the number of atoms per unit volume in the specimen. Okay, so if you look at the units, so the unit for cross section is going to be in centimeters square. Okay, so we are going to rely on the atomic model where you have the nucleus, which is positively charged, and then the electrons orbit around it in their different respective shells. And one of the things that I want to highlight here in the concept of understanding what cross section is that the cross section is not related to the size of the atom at all, right? So typically the size of the atom is about half a nanometer, so that's in the order of 10 to the negative 8 centimeters. But the cross section area is related to the process that you're trying to look at. So it could be as small as 10 to the negative 16, which is orders of magnitude smaller than the area of an atom or the size of an atom, or it could be as large as infinity, depending on what kind of scattering event you are trying to look at. Okay. So what is elastic scattering? Elastic scattering is very straightforward. You have learned this in basic fundamental physics. It is a process that involves no loss of energy and momentum. In other words, it is conserved. There can be a change in the direction of the electrons, but the magnitude of the velocity and the momentum does not change at all. Right? So elastic scattering of occurring through an atom was first studied by Rutherford, where he conducted the classic experiment of shooting alpha particles through a gold foil, where as a consequence of this experiment, he established the atom model, which is what we understand as the nucleus being centrally located, which is positively charged. There are neutrons in the nucleus, and then you have electrons orbiting around the nucleus. Okay, and the entire premise of the experiment was, if you shoot electrons, if you shoot alpha particles to the gold foil, the question that he tried to figure out was, why is there an angular dependence, right? So the angular dependence occurs because of the elastic scattering that the alpha particles encountered as they came closer to the atoms of the the nucleus of the gold atoms, right? So let's take a look at this. You have the target nucleus, right? And then you have a particle. In Rutherford's experiment, it was an alpha particle, but let's talk about electrons because we are looking at electron microscopy. So this is the target nucleus of your sample. Your electron comes along this direction. So the closest distance that the electron comes to the nucleus, or the closest perpendicular distance, is defined as the impact factor. And the angle by which the electron is deflected from its initial path is called the angle of scattering. Okay. So the impact factor, the square of the impact factor, is directly proportional to the cross section of the process, right? So if you look at this here, the expression from Rutherford's experiment, Q is the cross section of a scattering event to occur, resulting in a scattering angle greater than phi naught. And in this case, in this figure, it is theta, right? What this basically means is that's a measure of the probability that an incident particle or an incident electron will be scattered by an angle greater than phi naught. Okay, and this probability is proportional to the atomic number of the specimen of the atom and is inversely proportional to the square of the energy of the incoming electrons, right? So let's understand this through this simulation. So you have, this is a simulation of the Rutherford scattering experiment. There are going to be alpha particles coming from the bottom. This is the nucleus, and let's see what happens. So the alpha particles are now incident to the nucleus, and the nucleus has a positive force field. These are negatively charged, so the alpha particles just get deflected as a result of the elastic scattering, right? So now think of this as the electrons that are coming into a bunch of, in this case, there are 5 atoms, and then they get deflected, and some of them, if you notice, also bounce back, right? The electrons that are coming back, for example, this one right here was coming back. Those are called backscattered electrons, and they are very important in imaging this morphology of the surface. Okay, so let's move on to the next slide, so let me play this simulation here. In this slide, we are going to study the effect of or just understand the effect of atomic number, right? So before I play the video, the atomic number is determined by the number of protons and neutrons in the nucleus. You will see that I'm going to go back and forth and decrease and increasing the along this this bar here, and the atomic number, the square of that, is proportional to the cross section. So if you have a higher atomic number, the scattering is going to be larger, right? So that is what the simulation shows. I'm going to play it. Pay pay close attention to this. So at this moment, you have an intermediate number of atoms, protons and neutrons. Now, as I'm decreasing this, you will see that, which basically means that this is a light element, right? So the nucleus has less electrostatic force field. So the electrons are getting closer to the nucleus before they get elastically scattered. Now, if you increase this, so this is a heavy metal in the periodic table. Now you will see the electrons are not able to approach the nucleus as much, and there's a larger concentration of electrons that are sort of coming back. So if you bring it back to the initial values, that's an intermediate size atom, you have these electrons that are approaching the nucleus and getting scattered elastically. Okay, so let's move to the next simulation, which is the effect of the energy of the particle itself. So in this case, we are going to keep the atom and the neutrons, the protons and the neutrons in the atom constant. I'm just going to change the energy of the incoming particles, which basically means you're applying a different voltage to the electrons in the gun, right? And because the energy is inverse, the square of the energy is inversely proportional to the scattering cross section, you will see that for higher energy particles, they are able to approach closer to the nucleus, right? So let's play this video here. This is an intermediate energy. Now I'm going to increase it. So here are the incoming electrons. Well, in this case, it's alpha particles, but you get the idea. And now if you decrease the energy, they are much slower and they are unable to approach the nucleus at all. In fact, a lot of them get backscattered, right? So the simulation is available in the link that I have provided here. You can go and play around with the values and get a visual understanding of the process that's occurring here. Okay. All right. So now if you take this equation and you plot it as a function of the scattering angle itself, you will see, because it is proportional to the cot square, basically you get this line curve, which says that for processes where scattering angle is 0, your cross section diverges almost to infinity, right? And for processes where the theta is 180, the probability is very low and it approaches 0, drops to 0, right? So what this basically means is, if you have an electron and you expect 0 scattering, so there will be no scattering at all, that means the electron has to be very, very, very far, almost infinity in terms of those length scales of the electron and the atom itself, so that the atom's force field or the nucleus's force field does not affect the trajectory of the electron at all. So that's where this is, where you don't expect any scattering to occur, which in other words means that your scattering angle is approaching 0. Now, when you talk about a scattering angle of 180 degrees, that means the electron, when it hit the nucleus head on, or at least it did not hit it physically, but it approached the force field and then it just came back. So the likelihood of that happening is very, very, very low, which is understood in this line here, in the curve here, as it is approaching a very small cross section value of 10 to the negative 26, right? So if you look at, so this was just a theoretical curve. If you look at different elements which have specific z numbers or atomic numbers, you can see for a constant acceleration of the electrons or energy in the electrons, they have their own signature curves. So for carbon, which is significantly lighter than lead, has a smaller cross section compared to lead, which has a larger cross section, right? Because it is proportional to z square. Now for iron, as you increase the energy of the electrons, the cross section goes down, which is explained by the equation in the previous slide. Okay, so now when you're talking about scattering, the concept of mean free path is always associated with that, right? So for example, if you look at the conduction of electrons in a metal, we know that as you decrease the temperature of the metal, the resistance of the metal goes down, and that's simply because you're increasing the mean free path of the electrons. In other words, the electrons are experiencing less scattering as the thermal energy of the metal goes down, right? So this is something very similar to that. In this case, you define the scattering length or the mean free path of the electrons as a function of the Avogadro's number, the density, and the scattering cross section, right? So if you increase the Z number from carbon to uranium, you see that the mean free path is going down, right, for a given given energy of the electron. Makes sense because the scattering cross section here is going to be much smaller for carbon versus for uranium it's very high. Obviously the mean free path, which is inversely proportional to the scattering cross section, is much lower in uranium, right? So high Z correlates to, or high atomic number correlates to, an increase in the scattering cross section. But if the scattering cross section goes up, basically that means that the mean free path is going to go down. Make sense? Okay. So let's move on to inelastic scattering. So just to recap, the scattering, elastic scattering is related to no loss of energy and momentum. But inelastic scattering is a more realistic process that is going to happen because the electrons, as they impinge on the specimen, are going to lose energy, and as a result of which there are going to be multiple processes that occur. And the degree by which the electrons lose energy determine the processes and the various outcomes. Right? So energy is transferred to the tightly bound inner shells of the inner shell electrons or the loosely bound outer shell electrons, and that determine what happens. The amount of energy loss for electrons or gained by the atom can range anywhere between a few volts to kilo electron volts. That means all the energy, all the tens of kilo electron volts that the electron comes with could be lost in a single scattering event, or it could lose a few volts with one scattering event, move on to and hit the next atom, and subsequently lose the energy that the electron came with. Okay, and depending on the energy transfer, various processes occur within the specimen in a specific volume called the interaction volume. So we are going to talk about the interaction volume in the next class, but keep in mind that the electron, as it hits the specimen, just does not interact with one atom. It interacts with one atom, loses some amount of energy, and keeps going until it loses all the energy. Right? So the distance by which the electron traverses through the specimen determines the interaction volume. Right? And depending on the amount of energy lost, you can think of plasmonic excitation, secondary electron generation, inner shell ionization processes, Bremsstrahlung or continuum X-ray generation, or even phonon excitation. So let's take a look, a very, very qualitative look at each of these processes. So what is a plasmon excitation? Now, for metals such as aluminum or copper or gold or silver, which are highly conductive, you have very loosely bound electrons onto the atom. Essentially, you can think of it as a free electron gas, right? So now when you have the electrons that fall on these metallic specimen, the energy of the electron could be slightly transferred to the loosely bound electrons, typically very, very low energy, so about 15 electron volts or so. And as a result of which, these loosely bound electrons could start oscillating on the surface of the metal itself, which is called a plasmon excitation, right? So usually these plasmonic excitations have very high Q. Well, here Q is associated with resonance of the plasmonic excitation, so don't confuse this with the cross section. But usually, if these are very, very limited to a very small amount of metallic specimens, so they don't really they are not associated with the imaging of the specimen. Okay, so the other possibility is that you lose energy in the form the electrons lose energy so that they heat up the specimen, and the specimen as a consequence of that, it emits heat in terms of phononic excitation, right? So you have these high energy electrons that impinge on the specimen. Now, typically the specimen is very well thermally grounded, so the temperature rise is not tremendous. It is in the order of about a few degrees Celsius, and as a result of which the lattice oscillations are enhanced in the specimen, and energy is released in the form of heat, which is phononic excitation, right? So you can monitor the amount of heat that is coming out of the specimen and get information about the quality of the sample itself. Now, if you had a soft material, for example, a polymer, it's possible that the incident energy from the electrons is so much that the polymer melts all the way, right? And then that principle to some extent is used in electron beam lithography, where the incident energy, when it is incident energy of the electrons, when it impinges on the polymers, you can create these localized polymeric reactions, which is in other words called curing of the polymer, as a result of which you can create these patterns on polymer by sweeping the electron spot in a predetermined fashion. Okay. Then you have the generation of secondary electrons. So take a look at this schematic here. You have an incident electron with a certain amount of energy. It interacts with one of the electrons in the in the orbital system around the atom, around the nucleus, as a result of which it knocks the electron off. So you have a secondary electron generated, and this incident electron continues forward but with lower energy, right? So in case of semiconductors, you have the electron from the valence band that is knocked off, and it moves from the valence band to the conduction band in the picture of the band diagram. So you have the electron hole pair generation, so the hole remains in the valence band and the electron is now in the conduction band. If this were a metallic sample, then basically you're knocking off a conduction electron from the orbital, and then generating these secondary electrons. Now you can collect these secondary electrons that are generated from the atom itself, now undergo elastic or inelastic scattering, and some of them actually travel backwards and make their way out of the specimen, out of the surface of the specimen, and then they are detected by secondary electron detectors, and we'll talk about that in the future classes, right? But essentially, if you have an energy loss in the order of about 5 to 15 electron volts, you can generate these secondary electrons. So the secondary electrons can be also classified as slow electrons or fast electrons, depending on which electron in which orbital was knocked off. So if you have an electron that has been knocked off from an outermost orbital, then you end up getting slow electrons. But if you have the secondary electron generated from an inner orbital, you get a fast electron, because the amount of energy necessary to knock off this is really significantly higher than the amount of energy from an electron in the outer shell. Obviously, this electron begins with a lot of energy, so those end up going faster than the electrons that are knocked out of the outer shells. Okay. Then you have what is called the inner shell ionization. In this case, the electron interacts with an atom and causes the ejection of the tightly bound inner shell electron, right? And as the atom when it loses an electron, is ionized, and it's in a high energy state, which is not ideal. So what happens is you have an electron from an outer shell that moves from the outer shell to the inner shell, and because all of this is quantized, there is a signature X-ray that is emitted, right? So let's try to understand that in this image here. So basically what you have is an electron that has been knocked off, right? So you have an X-ray. So depending on which shell the electron has been knocked off from, you can have different X-rays. So as the energy is lost in the form of X-ray, now because the electron was lost from this orbital, it is replaced by an electron from the outer orbital, right? So when the electron moves from this orbital from the outer orbital to the inner orbital, there is a quantized energy transfer, and that quantized energy transfer is the energy of the X-ray itself, right? So depending on the material, depending on the atomic number, the amount of energy that an electron releases when it is moving from one orbital, one shell to the other, is characteristic of that material itself. So that would be so for example, if you think of sodium versus lead versus titanium, these are completely different atomic numbers, which means they have their own signature characteristic X-rays, right? So if you're able to excite or knock off the electrons from the innermost shell of these respective metals or elements, you have a signature energy transfer, so that they are replaced by electrons from the outer shell, and this is very important in the chemical identification process that is involved with electron microscopy. Okay. And the other possibility is that the electron that is coming into the sample experiences the force field of the nucleus, as a result of which, now one possibility is that the electron experiences the force field of the nucleus and just scatters inelastically, right? Elastically, which means it does not lose any energy. That is what we saw in a few slides ago. But the other possibility is that while the electron is approaching the nucleus, it sees the force field, and as a result of which it is constantly decelerated, right? It slows down. So which is all, and as it is slowing down, the electron loses energy, and it releases that in the form of X-rays, right? And this can happen over a wide range of energies, which is also why these are called continuous spectrum. Right. Let's look at this image here. This will make things a bit easier to understand. So you have a bunch of electrons that are approaching the nucleus, right? And for example, let's take a look at the electron which is labeled 3. This is coming head on to the nucleus. So this is decelerated the most, right? Because this is decelerated the most, it generates the an X-ray with the highest energy. Right? Higher energy corresponds to a shorter wavelength, which is depicted in this diagram. Now, for an electron which is slightly further away, let's say number 1, it also experiences the force field. It is scattered in a given direction, but while it is slowing down, it emits energy in the form of X-ray, which has low energy. So that has a longer wavelength. Now these are just some given examples, but this can happen over the entire range of energies, which is why the Bremsstrahlung scattering process, or the Bremsstrahlung X-rays, are also called continuous spectrum X-rays, which is different from the one that we saw in the previous picture here. These are called characteristic X-rays that are associated with the X-ray that is generated as an outer shell electron replaces an inner shell electron, right? So this is important for chemical identification. Don't confuse this with the Bremsstrahlung X-rays, which is a continuous range of energy that is emitted in the form of X-rays, right? So we will continue more with this and get a quantitative understanding of inelastic scattering processes and what is interaction volume, and we'll take a deep dive into the various processes occurring in the next class. Okay.